So we're now at the point where we can introduce the periodic table as a tool that we can use to attack chemical problems. You'll find the periodic table in two different places. It's slide 15 of your chapter 2 PowerPoint, and then I also uploaded it to D2L at the beginning of the course. So it's going to be useful to have that as a reference. So you either want to kind of print it out or have it open in another window so you can look at it as we talk about different things, or have it on another device. Just be able to reference the things that we're talking about on the periodic table, because again, you want to get comfortable using it as a tool, right? So just a little bit of sort of nomenclature from the start. The rows are called periods. Okay, so you kind of see that it's broken into a grid, and there are rows and there are columns. We call the rows periods, and we call the columns groups. Now, the groups are a little bit more important at this point in the semester, because the thing about the groups is that they all have similar chemical behavior. I shouldn't say all. In general, a group has similar chemical behavior. So if you go down a column on the periodic table, all right, like take 1A for example, all of those species are going to behave similarly when they interact with another particle. They're going to bond in a similar way. And so because they have similar chemical behavior, we call them groups, or sometimes we call them families, right? If you look at an entry, there's some information here that we can get, and all the entries are kind of organized the same way. We have the chemical symbol here in the middle, right? So I just picked boron B for an example. This 5 up here, the number without a decimal point, this is our atomic number. So this is our Z, right? And what you'll notice, just like we mentioned before, is that as Z increases, you get a different symbol down here, right? As Z changes, you get a different symbol down here, right? The Z is tied to a specific element, right? This number down here, this is our atomic mass. So the number with a decimal point, right, is the atomic mass. And we have to realize that at this point in the semester, we read that number as having units of AMU, right? Now, when we get to talk about bonding, which we'll actually do in a little bit here, all right, we're kind of close to being able to talk about a bonding intro. There are other important parts of the periodic table, so it's not just about realizing that there are rows and columns in terms of organizations and what information we can pull off of an individual block, right? We need to do some identification on types of elements, and what helps us do that is the staircase. And actually, if you look at boron, you'll see this bold line that kind of starts here and then goes down here, and then it kind of keeps going down the periodic table as a staircase. The thing about the staircase is it separates metals from non-metals. Now, metals and non-metals are going to behave differently when we actually get to, as I mentioned before, bonding, okay? So if you're looking at the staircase, I'm just going to kind of draw it over here, okay? On this side of the staircase, what we're going to have are metals. This periodic table kind of tells you that, but it's just good to know because some periodic tables don't have that information on it. On this side of the staircase, we have non-metals, right? Metals and non-metals. When we get to bonding, one of the first steps that we do is identify metals and non-metals, and you literally just look on which side of the staircase they are. Now, your periodic table has this green bit of this green grouping of elements that are near the staircase called metalloids. Don't worry about metalloids, okay? So literally when we do problems, the way I want you to think about it is just consider metals and non-metals, and metals are anything to the left of the staircase and non-metals are anything to the right, right? There are some important groups that we need to talk about, okay, because we'll be referencing them by their group name. They're just so prevalent in chemistry that, again, they just have this nomenclature that we need to be able to adapt to. Group 1A, these are called the alkali metals. These are definitely metals. We see that it makes sense because of where they are relative to the staircase. The thing that we need to know right off the bat about group 1A is that when they're involved in ionic compounds, they like to be +1 in charge. Okay, group 1A, when they're involved in ionic compounds, when they make a bond, right, they like to be +1. Group 2A are the alkali earth metals, and these guys like to be +2 when they're involved in ionic bonds, right? Now you see this big chunk of the periodic table in the middle, and it looks like it's kind of separated out as like its own little block. And instead of having a label with an A associated with it, it's going to be a set of numbers and then B's, right? 3B, 4B, 6B, etc. These are the transition metals, right? And the thing about the transition metals is that we kind of lose a pattern here. There is no pattern, and in fact, one particular atom can have different charges. For example, iron is in this block, and iron is sometimes +2, and iron is sometimes +3. And that's the case for most of the metals in there, and you can get different charges. So just to recap, the nice thing about groups 1 and 2 is, yep, they're metals, they form positive charges, but you know their charges. Anything in group 1 is always +1. Anything in group 2 is always +2. But whenever you hit this transition metal block, this B block, there's no pattern there, right? And in fact, one species can have different charges. So we're actually going to need to put more information into our names when we get to nomenclature to actually account for this, okay? The only other thing I want to point out about the transition metals is that tin and lead are technically not in this B block, but they have this this sort of situation where they can have multiple charges. And so for all intents and purposes, these guys are transition metals. So even though they're outside of the B block, just always remember that tin and lead, they behave like transition metals, so we call them transition metals, even though they're not technically inside there. All right. The next group I want to mention are the halogens, right? They're in group 7A. They're fluorine, chlorine, bromine, iodine, all right? Astatine. So these guys, all right, when they form ionic compounds, all right, they like to be -1. Right? Now we can actually kind of remember that idea that 7A is -1, and you can take steps backwards. And what I mean by that is, I just need a little bit more room here. So you can write down in your notes, but I just need a little bit more room. See how we kind of step forward with group 1 and 2, we go +1, +2, all right? We can keep stepping forward, and when you get to 3A, what you're gonna have is a bunch of situations where the metals in that group, if they're involved in ionic compounds, are all gonna be +3 in their charge, right? Stepping back from 7A, group 6A, which has a name, but we don't really need to know it. This is what I'm going to refer to as the oxygen group. These guys like to be -2 in charge when they're involved in ionic compounds, right? Group 5A, these guys like to be -3 in charge when they're actually involved in ionic compounds, right? Now, the only group we haven't really referenced then is group 4A, and group 4A is kind of weird. Group 4A does contain tin and lead, right? Tin and lead. And group 4A starts with carbon, and carbon is generally going to be involved in covalent compounds, okay? So when you look at a periodic table, these numbers attached to the actual group mean something. They tell us that there's similar chemical behavior underneath, all right, that number. There's similar chemical behavior down that group. And then there's information that we just need to be able to look at in terms of the periodic table and pull off in terms of charges in dealing with ionic compounds, all right? So one last recap, group 1A, +1 when they're involved in ionic compounds, 2A, +2 in ionic compounds, 3A +3 in ionic compounds. 4A, right, contains tin and lead, which are really transition metals, where we don't have a pattern and we have multiple charges inside that group, all right, even for one particular element. Group 5A, -3 in ionic compounds, 6A, -2 in ionic compounds, 7A, -1 in ionic compounds, and 8A are noble gases. Sometimes these are called the inert gases. And these tend not to bond, right? So we don't even say that they have a charge associated with ionic behavior. If they do bond, they will form covalent compounds. You might have heard in high school that they never bond, but that's not true. And we'll see later on in the semester that there are some bigger sort of gases in the inert gas section that can actually form bonds, all right? So even with this periodic table introduction, we were mentioning things like covalent and things like ionic. And so that kind of leads us to, all right, that's just information now. It's just like a word that you've been told without a meaning. And so the next thing that we want to do is we want to do an introduction to bonding, so that words like ionic and covalent mean something. So right now, like I said, it's just information that you should be able to find on the periodic table, but how do we use that information? Well, we understand how bonds are actually formed. Remember back at the beginning of the semester, we would kind of draw these circles and we would say that, oh yeah, there's a bond that occurs between these two objects, right? And we said, don't really worry about what's going on inside there. But somehow these guys are attaching to each other, right? There actually ends up being two main types of bonds. So there are two types of attachments that could possibly occur, right? And the first one that we're going to talk about is one that we referenced when we were going over our periodic table introduction, and that's an ionic bond. Ionic bonds, all right, involve ions, okay? So these are cations and anions, all right, attracted to each other. So the way that you view this coming together, this bond, is that you have something that's positive and something that's negative. And if these guys were far away from each other, they would actually start to feel each other. And we know that positives and negatives, these are opposite charges, they attract. And so they would actually kind of get into a situation where they were right up next to each other. So it really is like one whole separate cation and one whole separate anion, all right? Just coulombically bound to each other, just with charges stuck together because opposite charges attract, all right? Ionic compounds then, all right, are always these neutral structures where the pluses and minuses are balancing each other out, all right? We'll see some structures where if this is a +2 cation, say it's an alkali earth metal, how many negative ions will we need to balance it out? We would need another negative to balance it out, right? So even though there are ions involved, whenever you look at the overall structure, the pluses and minuses cancel to give you a neutral compound, right? Now ionic bonds and ionic compounds, these are formed when a metal interacts or bonds with a non-metal. So when a metal and a non-metal attach to each other, when a metal and a non-metal bond, that's when you get an ionic bond. That's how you know that you have cations and anions attracted to each other. It's really all about metals, right? Our first identification step to whether we have an ionic bond or not is we're going to say, hey, do we see a metal? All right, do we see a metal? As an example, a classic ionic compound example is NaCl, sodium chloride, which is a main component of table salt. If you look at sodium chloride, right, we'll figure out how to name it later. What we see here is it's definitely a compound. It's two things stuck together, all right? I look and I do my identification step, and what do I see? I see sodium. Sodium is in group 1A, right? It's an alkali metal. As soon as you see a metal in a compound, you know right away it's ionic, right? So this is an ionic compound. So how do we view the formation of this guy, all right? The way that we view this is Na, all right, normally has a certain number of electrons, but Na is in group 1A. So what does it like to do? It takes one of its electrons, right, and it likes to get rid of it. Now, how do I know that based off its position on the periodic table? We learned that in group 1A, Na likes to be +1. And in fact, anything in group 1A likes to be +1. Well, how do you be +1? You get rid of an electron, right? Cl, on the other hand, excuse me, is a halogen. It's in group 7A. What did we just learn about group 7A? They like to be -1, right? They like to pick up extra electrons, okay? So if this wants to be -1, this electron that is leaving Na, because it wants to get rid of it, will go to the Cl, okay? So based off the position in the periodic table then, what happens is Na gives up its electron and it becomes a full positive charge, right? And Cl gains an electron and it becomes a full negative charge, all right? So for ionic bonds, the way that we want to view their formation is electrons are exchanged. Metals want to be positive, and so they'll give up to their electrons to non-metals that want to be negative, right? And then what you'll have is a balance of charge in the whole entire structure. You'll have an Na that's plus and a Cl that's minus, and now they're bonded together, okay? Now, why don't I show a plus or minus here? Inside these formula, if there's no overall charge, you don't show charge, but we have to know that based off a position on the periodic table, Na would be plus and Cl would be negative, okay? One other quick ionic example. Let's look at something like FeI2, Fei2. So here, do we know if there's an ionic bond or not? I look at Fe. Is it in one of my groups that I consider a metal? Is it to the left of my staircase? And the answer is yes. Fe is a metal, so then right away you know you have an ionic bond, all right? Well, we just got done saying that Fe is in a special category of metals called transition metals, and Fe might have different charges. It's not as straightforward as sodium, where sodium Na is always +1. So how am I going to know the charge of this Fe? I definitely know it has a charge because it's a metal bonded to a non-metal, all right? But how do I infer that charge? Well, we can look over here. And what do we see? We see that I is a halogen. And what do we know about halogens? We know that halogens exist in group 7A, and they like to be -1, all right? So there's two -1s here. So what does that mean about Fe? That means that this particular Fe must be +2, right? So hopefully you can follow that logic, but then in your head, right, the picture of the bonding looks like this. Here's my Fe +2. It must have given up 2 electrons. Where did those electrons go? One of the electrons went to an I, and it became I-, and the other electron went to the other I, and it became I-. I have a +2 and I have 2 minuses. I get a total charge of 0. That's how we view this this compound right here, which is actually iron 2 iodide. Don't worry about naming quite yet, but that's what this actual compound looks like from the fundamental standpoint of balancing charge, all right? So ionic bonds are all about exchanging electrons, making ions that then want to be close to each other. They want to be stuck to each other, all right? These are actually really strong bonds, all right? They're very strong bonds, right? So what happens when we don't have a metal? You know, I just kind of mentioned over and over again that when we look for ionic characteristics, you look for the presence of a metal. If there's no metal present, then what you have is a covalent bond. All right? So this occurs when two nonmetals interact with each other, when two nonmetals bond. And here's the thing with a covalent bond. There are no ions, all right? So even though we know information from the periodic table about what the halogens might be in terms of their charge and what oxygen's group might be in terms of their charge, there are no charges here. It's a different type of bond. This bond is formation process is completely different, and in fact, for a covalent bond, electrons are shared. Right? Electrons are shared. So they're not exchanged anymore, they're shared. This is actually a very complicated process from the physics standpoint. All right, it's very complicated. All right. What you'll see is that on slide 19 of your chapter 2 slideshow, you'll kind of see how it's complicated. There's a lot of different interactions going on. Don't do anything else besides just kind of look at that and say, oh yeah, there are a lot of interactions going on. It's a lot more complicated process. That's all we really have to know right now. All right. There's quantum mechanics involved with understanding what happens, and we're not quite there in the semester to even bring up the just basic ideas of quantum mechanics to understand what's going on. All right. What you need to know now, just focus down on the idea that when you see two nonmetals together, all right, what you have is a covalent bond. If you don't see a metal in a compound, then the electrons inside it are shared, and we call that covalent. Just a couple examples. All right. Things like O2 gas, right? Oxygen is in group 6A. It's to the right of the staircase. O2 means that you're actually kind of bonding together two of a type of a molecule, two atoms of oxygen, all right? Two atoms of oxygen are bonded together. Is there a metal present? No. So then if there's no metal present, it's covalent. At this point in the semester, we don't even try to draw, all right, what this looks like, all right, because it's so complicated of a process. But what we have to know is that they're stuck together through a sharing of electrons. So it's not a plus and a minus anymore. The electrons in between the atoms are being shared, right? It's covalent. We can also look at carbon monoxide and carbon dioxide. And this brings the point of the complicated nature of the process up to light here. Sometimes carbon can bond with oxygen, right? And we get one C and one O stuck together, all right? Sometimes carbon bonds with oxygen and we get one C and two O stuck together. And that's just based on the complicated nature of covalent bonding, on the sharing of electrons. Are there any charges here? Nope. Are there any charges here? No. Are there any charges here? No. There are no charges present. There are no ions, right? Carbon and oxygen, they're both nonmetals. So just like O2, these guys are also covalent. Now, when we get to naming, right, because carbon and oxygen bond in different ways, we actually have to include a lot more information in our names because of this. So the more complicated the bonding, the more we can't pull information from the periodic table about what's occurring. And we're not just balancing charge here. There's this complicated electron sharing process occurring, right? The more complicated the bonding, the more information we put into our names, right? And that's actually something that we'll talk about on the next video. We'll eventually get into, now that we understand a bit about the periodic table and a bit about bonding, ionic versus covalent, we can start to talk about the names that we see out there in the real world and in science related to molecules and compounds, okay? We'll actually get into chemical nomenclature next time.